Okay, in this video lecture, I want to have some clarifications about multiple uses of the same type of quantifier, and in particular, one of the ways in which we have to be careful to express distinctness. So if you look at a sentence, for example, that says this, suppose we have there exists x, there exists y, such that cube x and cube y, that's a y right there. You might think that this actually implies that there are two different cubes. And as far as conversations go, you'd be right in thinking that, right? But that's a conversational implicature. It's not strictly speaking part of what's being said. If we want to say that there are in fact two distinct objects, we need to use an identity claim. In particular, what we need to do is say that the x and the y are not identical to each other. So we need to add an additional statement that says, and x is not identical to y. And that statement now will tell us that there exists at least one cube and there exists at least one y cube, and those two are not the same. That's how we can express the distinctness of those two claims. The same thing will go with universal quantifiers. One of the things that you should see in the you try it sections is having to play around with this distinctiveness in interpreting those types of claims. So for example, if I have the claim that says for all x and for all y, if x is a cube and y is a cube, so I want that condition to be met. So I'm actually going to need an additional set of parentheses right in here, right, to indicate that's going to be the antecedent to conditional, right? So I've got this here is the antecedent to that conditional. Now I'm going to say that x is left of y. And this parentheses out here is the one that connects all the way out there. So here again, you might think that this sentence entails that there have to be two different cubes. But that's in fact not the case, not unless we add into this sentence the claim that x and y are not identical to each other. It's possible that x and y are picking out or denoting the same cube. So here's a way that I typically think about universal quantifiers. When I'm thinking of this first universal quantifier, I'm saying, okay, I have to go through my domain and I have to look at every single object in my domain and make sure some conditions are met. And while I'm doing that, as I pick up each object in my domain, I'm then asking again to pick up each object in a domain. But you can always look at the same object that you picked up the first time. We haven't been told that we have to look at all other objects, right? So, I'm currently looking at one object, making sure that it bears relations to all objects in the domain, including itself. That's always possible. So if I have, for example, a domain where there's just one cube, so I'm now looking to see, okay, given that x is a cube and given that y is a cube, I can temporarily use x to denote the cube and use y to denote that same cube. And then, so that would satisfy the antecedent of this conditional. But the consequent here, that x is left of y, would be false, right? Because an object can't be left of itself. So if I wanted to say, for example, that every cube was left of every other cube, I'd have to use an identity claim to make it clear that there is a distinct set of objects or pair of objects that I care about. Now that type of sentence as well is going to be difficult to do in the kind of domain that we currently have, because we on our grid have a maximal point that you can be to the left of. But if we imagine sort of a funny scenario where you're imagining the globe, for example, you want to sort of say something like, or you want it to be possible to say like, well, every cube is left of every other cube, including itself, if you wrapped all the way around the world. Now, we're not going to consider those types of, odd cases. We might want to, in this case, say something like, every cube is left of or right of every other cube. So in that case, what we would want to do, right, is add to this sentence, we'd want to say something like, x is left of y or right of x, y. Right, and that might be a case where we're trying to describe a world where every cube, like none of the cubes are in the same column, right? That they're all left of or right of every other cube. Still here, it's important, right, that I said of every other cube, right? So to keep sort of things simple, what I have to make sure I do is add an additional clause which says, and x is not equal to y. Now, right, when I pick out use x to denote this cube, y can't pick this out because x and y have to be distinct. So y would have to pick out that cube. And now this sentence will be true, right? Every cube is going to be either the left of or right of every other cube. So in the case when x picks out the left one, it's true that x is left of the one on the right. And the same possibility has to hold, right, if I had assigned y to the left cube, and if I had used x to apply, to denote the cube on the right. So the key thing here to notice is that when we add these types of additional clauses, what we mean is, say, a pair of objects and some relation that holds between those pairs of objects, pairs of distinct objects. So that's going to be important to recognize when you have to use the non-identity claim. Most of the time, this work is done for you. If instead of cube, it said tetrahedron, you know by the meanings of the predicates that if something's a cube, that rules out the possibility that it's a tetrahedron. And same thing up here with the existential quantifier. So a lot of the times we won't need to add the non-identity claim because it's already given to us as an entailment of using the predicates cube and tetrahedron. It's the meaning of those predicates that we know that they can't pick out the same object. Okay, so that's additional clarification on how we can use multiple quantifiers of the same type to use them in addition with the work of identity or the negation of identity to talk about distinct objects.